All right, hey there, everybody. So we're starting a new unit on waves and simple harmonic motion. And you probably have a pretty good idea what a wave is already, but in physics we have a specific definition of that. And so we say that a wave is a disturbance that transmits energy but not matter. And so you can probably think of a few different examples of waves. You might know that light travels as a wave, or sound travels as a wave, or even just waves in the water. Now, each of these are examples of things that are transmitting energy, but at the end of the day, there's no matter that's being brought along the entire path of the wave. So there's two types of waves we're going to look at in this course. And the first is transverse waves. And a transverse wave probably looks kind of like what you think of when you think of a wave. And the thing about a transverse wave is that the motion of the wave, the propagation of the wave, is perpendicular to the motion of the particles in the wave. If you thought about a little particle on this wave, it might be moving sort of back and forth this way, but the overall propagation of the wave or motion of the wave would be to the right. And so a transverse wave, the particles move perpendicular to the wave propagation. Examples of this might be things like light waves. By comparison to that, we also have longitudinal waves. And longitudinal waves are compression waves. And so what we have is, if you imagine if you took like a slinky and you pushed it, you might have an area where the waves really spread out, followed by an area where the waves really compact, and the spring is more spread out, and then really compact, and spread out, and so on. And so these waves, again, are propagating, in this case, let's say to the right. But the individual particles inside this slinky will be just sort of moving back and forth, shifting back and forth. And so in this case, the motion of the particles that make up the wave, or the wave medium, are traveling parallel to the actual wave propagation. And a good example of longitudinal waves would be sound. So if we look at just an example of a wave here really quickly, you'll see that if I disturb this string, that whichever way I move this string, essentially a wave propagates or travels through the spring. Now that's a single pulse. A single pulse of a wave just happens when you have a single disturbance, and that pulse travels along through the wave. If I continuously move the medium back and forth, if I continuously move the string back and forth, then I might get an oscillation, which is like a regular repeating back and forth motion. I'm just going to hit slow motion here just to see things move down. So you might, when you take a look at this wave, you might recognize that this is in fact a transverse wave. You can see the individual particles here are just sort of moving back and forth, whereas the wave itself is propagating itself to the right. Now, if we take a look at that kind of wave, there's a whole bunch of different properties of waves that we're going to look at, or quantities. So if we draw out a wave, and these are true for both transverse and longitudinal waves, but I'm just going to draw a transverse wave to use that as my model. The first thing here is the medium. And the medium is the material that a wave propagates through. So it's literally whatever the wave travels through. In the case of sound, the wave might be traveling through air. In the case of light, it might be traveling through the vacuum of space. And in the case of a string, well, then the string itself would be the medium. On this wave here, we have crests and we have troughs. And the crest is really just the high point, the highest point, and the trough is our lowest point. Now, in addition to the wave itself, you can also imagine that this wave has like a little equilibrium point. So if we imagine this being like a string, like in that animation there, this equilibrium point is the point that where the string would just rest if we weren't moving it back and forth. This equilibrium point would be the point that the string would rest at if we weren't moving it back and forth. And so the displacement from equilibrium, this distance here, we call amplitude. Now, you might look at this picture and think to yourself, well, the distance from the equilibrium point to the crest is probably also the same as the distance from the equilibrium point to the trough, and you'd be right. The last thing we're going to look at here is wavelength. So the wavelength of a wave is the distance traveled by one complete cycle of the wave. And it gets the symbol lambda, which is a Greek letter. It looks like an upside down Y. So this is the distance traveled by one complete cycle. Okay. So, in addition to these terms, we've got a few other terms that we need to get used to, and those are period and frequency. The period of a wave, capital T, is really a measurement of time. And so the period is the time for one cycle. And the frequency is the number of cycles per second. Frequency is measured, time period is measured in seconds, and frequency is measured in hertz. And frequency and period are reciprocals. So by that I mean the frequency of a wave is just 1 over the time period, or vice versa. The time period is 1 over the frequency. Now, if you think about a wave, let's just go back to our example here really quickly. So this wave is propagating through the string. And you might think to yourself, well, that wave has a certain speed, which tells us, well, how fast the actual wave is traveling along that string. You might wonder how these different factors will affect the speed. So for example, what happens if I increase the amplitude of my wave? If I have a really big amplitude wave all of a sudden? Well, if you look closely enough, these larger amplitude waves compared to those smaller amplitude waves, the larger crests aren't really gaining any ground on the smaller crests, or vice versa. So in actual fact, the speed that the wave travels through this string has nothing to do with how tall the wave is. The taller waves have more energy, and you could imagine being maybe hit by water waves on the beach. The taller the waves are, the more energy they have when they hit you. But the actual speed of the waves don't seem to depend on how tall the waves are. Now, the other comparison is frequency. A high frequency wave is one where the source is moving back and forth very, very quickly. So this would be a higher frequency wave. And we could compare that to a lower frequency wave, something like this. And again, while at first glance you might think that higher frequency waves might travel faster, you can see that's actually not the case. These lower frequency waves, if I send some higher frequency waves after them, the high frequency waves don't catch up. They all propagate at the same speed. So frequency and speed aren't necessarily related. What is related, though, you'll notice, is as I drop the frequency of the wave down, what changes as a result is the wavelength. So this would be a low frequency wave, and you can see it has a really long wavelength. And by comparison, these waves have a much higher frequency, but have a much shorter wavelength. So let's do this problem right here. Playing middle C on a piano produces a sound with a frequency of 256 hertz. What is the period of the sound wave? Well, the period of a sound wave is 1 over the frequency, which is 1 over 256, which in this case would be 0.00390 seconds. So what that means is, when you play middle C on a piano, the wave that propagates through the air as a result causes those air molecules to vibrate back and forth very quickly. They vibrate back and forth in just a time period of just about 4/1000ths of a second, which is very, very quick. Now, you remember from kinematics that the speed of a wave, the speed of anything, is just defined as distance over time. Well, if you look at a single wave, the distance traveled by a single wave would be equal to the wavelength. And the time it takes to travel would be equal to the period. And so we could convert this formula to say that speed would just be wavelength over period. But if you remember, since period equals 1 over frequency, this gives us something called the universal wave equation, which says that the speed of a wave is equal to the wavelength times the frequency. And whereas v is speed, lambda is wavelength, measured in meters, and frequency, f is frequency, again measured in hertz, or 1/seconds. And so you can see the units there are going to be just meters per second. Okay, so let's try this formula out with a couple of examples. So an air horn sounds at a frequency of 220 hertz. The speed of sound in air is 330 meters per second. What is the wavelength of the sound wave? So if speed is equal to lambda f, then lambda must be equal to v divided by f. And so we can substitute in 330 meters per second divided by 220 hertz. And so our answer would be 1.5 meters. All right, let's look at this next one. The distance between successive crests in a series of water waves is 4.0 meters, and the crests travel 8.6 meters in 5 seconds. Calculate the frequency of a block of wood bobbing up and down on these water waves. Okay, I'm going to draw a little picture here because I don't really know if I fully understand what this is saying. So you have a series of water waves, and we've got like a little block of wood here that's kind of like just bobbing up and down on the water waves, riding it as the waves go by. Now the distance between successive crests, meaning one crest after the other, the distance from there to there is 4 meters. But when somebody was measuring these waves, they found that it traveled a total of 8.6 meters in 5.0 seconds. So the first thing you might recognize here is that really this distance here, 8.6 meters, this really is just a distance. It doesn't tell us anything special about the waves. Whereas this 4 meters is the wavelength. It's the distance from crest to crest, or the distance traveled by exactly one wave. So to find the frequency, maybe first we could find the speed. We know that speed is equal to distance over time. So 8.6 meters divided by 5.0 seconds gives us a wave speed of 1.72 meters per second. If we now turn to our universal wave equation, where speed is equal to wavelength times frequency, we can see that frequency will just equal speed divided by wavelength, which is 1.72 divided by 4, which gives us a final answer of 0.43 hertz. All right, that's it for lesson 1.